We have already completed no bias condition of PN junction diode. In this lecture, we will discuss forward bias condition of PN junction diode. Under no bias condition, we do not apply any external voltage source across these two terminals. So this is the case of no bias condition. And let's say the width of depletion layer is W subscript D, and this is the junction, and we have diffusion current from left to right. And I will call it I majority, and we have reverse saturation current from right to left. This is I subscript S, and reverse saturation current is due to the minority charge carriers. Now in forward bias condition, we connect positive terminal of the battery to the P side, and we connect negative terminal of the battery to the N side of the PN junction diode. So I will do this quickly. This is the positive terminal of the battery and this is the negative terminal of the battery, and I will connect the positive terminal to the P side of the PN junction diode, and I will connect negative terminal to the N side of the PN junction diode. Now because of this, the holes on P side will be repelled, because holes are positively charged and we have holes as majority charge carriers on P side. This positive terminal of the battery will repel the holes towards the depletion layer, and in the same way negative terminal of the battery will repel the electrons towards the depletion layer, because electrons are negatively charged. Thus we can say that the forward bias potential VD will pressure the electrons on N side and holes on P side to recombine with the ions near the boundary and reduce the width of depletion region. So the width of depletion region will reduce because the holes will combine with the negative ions and electrons will recombine with the positive ions. So we have holes recombined with the negative ions, and we have electrons combined with the positive ions. And as you already know, in depletion layer we do not have mobile charge carriers but we have immobile ions. So the width of depletion layer will reduce and we have a new depletion region, and let's say the width is this is the new width, and I will call it WD prime. So we have new width equal to WD prime, and if I compare it with no bias condition, then VD was equal to 0 and the width of depletion region was W subscript D, and when VD is greater than 0, it means it is positive. The new width is WD prime, and if we compare WD and WD prime, we will find WD is greater than WD prime. So we can say that on increasing the bias potential, the width of depletion layer will reduce. This is very important point. On increasing the bias potential, the width of depletion region will reduce, and in this case we have diode current ID, because circuit is complete and we have current ID, and if you want to calculate ID, then ID is equal to I majority minus I saturation, where I majority is the diffusion current because of majority charge carriers and IS is the reverse saturation current because of minority charge carriers. Now what about reverse saturation current? What will be the effect on reverse saturation current because of the forward bias potential? If you remember, in the first lecture I told you the number of minority charge carriers depends only on temperature. If temperature increases, minority carriers will also increase. So if temperature is same, the number of minority charge carriers will also remain same. So we can say that the reverse saturation current will remain the same, because temperature is not changing and it only depends on the minority charge carriers. But there is change in diffusion current. The depletion layer is reducing because of the applied forward potential, and the electrons on n side will see a reduced depletion layer, and also it will be attracted towards the applied positive potential on the p side. So there are two things happening. The first thing is the width of depletion layer is reducing, and hence we can say that the barrier potential is also reducing. Let me write this down. Width of depletion layer is reducing, so the barrier potential is also reducing. And let's say initially the barrier potential was VB. So the new barrier potential is equal to VB minus VD, where VD is the applied forward bias voltage. So the new barrier potential is VB minus VD, and in case of silicon, VB is equal to 0.7 volts. We calculated this in the last presentation. The barrier potential for silicon is equal to 0.7 volts, and if I make VD equals to 0.7 volts, then the new barrier potential is equal to 0.7 minus 0.7, and this is equal to 0 volts. So the barrier potential is decreasing with increase in the forward bias voltage, and an electron on n side now sees a reduced barrier at the junction and a strong attraction for the positive potential applied to the p side. As the magnitude of the applied voltage increases, the width of depletion layer continue to decrease until a flood of electrons can pass through the junction, and because of this there is an exponential rise in diode current ID. Now I will quickly revise all the points. The first thing in forward bias condition is the connection. The positive terminal of the battery or voltage source is connected to the P side, and the negative terminal of the battery is connected to the N side. Positive terminal of the battery will repel the holes towards the depletion region, and negative terminal of the battery will repel the electrons towards the depletion region. There is recombination of immobile ions and mobile charge carriers, and because of this, width of depletion layer will reduce, and also the barrier potential. Once the barrier potential is equal to 0, the flood of electrons will pass through the junction and the current rises exponentially. And also there is one important thing regarding the reverse saturation current. The reverse saturation current remains the same because the minority charge carriers only depends on temperature. All these points will be helpful when we draw the VI characteristics or volt ampere characteristics of PN junction diode. We will use the knowledge from this lecture to plot the VI characteristics in forward bias condition, and in the next lecture we will discuss reverse bias condition of PN junction diode. So this is all for this lecture. See you in the next one.